Hello everyone. In this video, we're gonna learn how to prove the compound interest formulas, and then we're gonna explore some examples. Alright, so first, we know that we have the simple interest formula. It's gonna be I equals P times R times T, right? This is very simple, right? Because whenever you deposit some money into the bank, right, with the interest rate and with the time T, and then the simple interest formula, you just take P times R times T, right? Now, keep in mind R will be calculated as decimal. What if the interest rate right here is compounded n times per year? For example, half year, quarterly, monthly, daily, or something like that, right? So the time of each compounding period is 1 over n years. Alright, so we just rewrite this formula as I equals P times R times 1 over n, right? Now, the ending amount is the principal plus the interest. So it's going to be equals principal plus P times R times 1 over n, right? Now, this one can be written as P plus P times R over n, and then you factor P out, so it will be P times 1 plus R over n. So this is the amount after one compounding period. Now after two compounding periods, this guy becomes the new principal. Now this one can be written as P times R over n, right? Now we have the new ending amount after two compounding periods. It's going to be new A. It's going to be equals the new principal, which means P times 1 plus R over n, right? Plus the new interest. The new interest is the new principal multiplied by R over n, right? So plus P times 1 plus R over n multiplied by R over n, right? Now I'm gonna factor this guy and this guy out. So it's gonna be P times 1 plus R over n, right? Now the first one right here I have 1 left. The second one right here I have R over n left. Alright, so this guy turns out to be P times 1 plus R over n squared, right? Now, if you keep doing the same process, you're gonna end up with, after 3 compounding periods, the amount of A is P times 1 plus R over n power of 3, right? Now, if you keep doing the same way, after n compounding periods within 1 year, the amount of A is P times 1 plus R over n power of n. Because t years will contain n times t compounding periods, so after t years we have A equals P times 1 plus R over n altogether power of n times t, right? So this is the proof of the compound interest formula right here. Now we're gonna prove this formula. Now we have the amount of 1 year, which means t equals 1, right? So the formula becomes A equals P times 1 plus R over n raised to the power of n, right? Now this one can be written as P times 1 plus 1 over n over R all together power of n, right? Now we just rewrite this one as P times 1 plus 1 over n over R, right? All together. Now, remember we have a power of m, all together power of n is going to be a power of m times n, right? So, this guy right here, n right here can be written as n over r. All together power of r outside, right? Okay, now I'm gonna let k, p, n over r, right? So I substitute over here. So this guy turns out to be p times 1 plus 1 over k, all together power of k and power of r outside, right? Now, suppose that the number of n of times that the interest is compounded per year gets larger and larger, which means when n approaches infinity, and then this expression right here, k approaches infinity, right? Because k equals n over r, right? Now, we need to find the limit of 1 plus 1 over k all together power of k when k approaches infinity. Alright, now we need to prove this one equals e, right? So how do we prove it? Now we know that a number a can be written as e to the natural log of a. This one can be written as limit when k approaches infinity, right? So it could be e to the natural log of 1 plus 1 over k raised to the k, right? Now we know that log base a of b power of k. So you can print k to the front, it's going to be k log base a of b, right? So I can bring k to the front. This guy turns out to be limit when k approaches infinity e to the k natural log of 1 plus 1 over k. This one can be written as limit when k approaches infinity e to the power of k. You can bring it to the bottom right here by divide 1 over k, right? So it can be natural log of 1 plus 1 over k over 1 over k, like that, right? This is e to the power of this one. Keep that in mind, it's not multiplied. This is e to the power of this. Now I let u be 1 over k, right? So when k approaches infinity, u approaches 0, right? So this one can be written as limit u approaches 0 of e to the natural log of 1 plus u over u, right? Now this guy can be written as e to the limit of natural log of 1 plus u over u when u approaches 0, right? So when u approaches 0, the numerator approaches 0, denominator approaches 0, and this is indeterminate form, right? So we can use L'Hospital rule, right? So it turns out to be e to the limit when u approaches 0. Derivative of natural log of 1 plus u is going to be 1 over 1 plus u, right? Derivative of u is going to be 1, right? So this guy turns out to be 1 over 1 plus u, right? So when u approaches 0, this guy approaches 1, right? So the whole thing approaches e, right? So we just prove that this guy right here approaches e when k approaches infinity, right? So this guy can be written as p times e to the r, right? So finally we have a equals p times e to the r. The amount a after t years due to a principal p invested at an annual interest rate or compounded continuously is a equals p times e raised to the r times t, and this is the formula, and we just prove the formula. Now let's take a look at the first example. We need to invest 1,000 at an annual rate of 10% compounded annually, right? So this guy is P, right? Because this is the principal, right? This is the compounded interest rate, right? So this is R equals 10% or 0.1. Now, semi-annually, which means n equals 2, right? Semi-annually, which means half year. Quarterly, 1 year has 4 quarters, right? So this guy n equals 4. Monthly, 1 year has 12 months, right? So n equals 12. Daily, 1 year has 365 days, right? So n equals 365 days. Now t equals 1 year, right? Now we just apply the formula right here. So we have the first one is going to be semi-annually, which means half year, right? So a equals p, which means 1,000 times 1 plus 0.1 divided by n is going to be 2. Raised to the 2 times 1, right? Because t equals 1. So the answer is 1,000 times 1 plus 0.05 power of 2. And then it's going to be 1,000 times 1.05 power of 2, right? So we're going to print up the calculator. The answer is 1,102.5, right? Dollars. Now, next one, quarterly. So n equals 4, right? This is n equals 2. N equals 4, so a becomes 1,000 times 1 plus 0.1 divided by 4 power of 4, right? So now we're gonna bring up the calculator. So it's gonna be, so the answer is 1103.8. 1103.8, right? So now next one, monthly, which means n equals 12, right? So a equals 1000 times 1 plus 0.1 divided by 12 raised to the 12, right? The answer is 1104.7. Now, the last one, daily, which means n equals 365. So a equals 1000 times 1 plus 0.1 divided by 365 raised to the 365, right? It's going to be 1105.2, right? So approximately $1,105.2. The last one, what if the annual rate is compounded continuously, right, for a time t of 1 year, right? So we're going to use this formula right here. So it's going to be a equals 1000 times e raised to the 0.1, right? Times t equal 1 because we only have 1 year, right? So we bring up the calculator. So the answer is 1105.2, right? It's approximately $1105.2. Alright, keep that in mind. This formula is used for compound interest. This one is used for continuous compound interest. And it's your time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand in mine.